Hello everybody, and welcome to a new episode of Back to Basics. Last week we talked about half-wave rectifiers. This week we're going to talk about two different ways to make a full-wave rectifier. Now the first way is terribly inefficient, and you'll see it in a lot of older power supplies, and they're going to look a little like this. And in fact, on Wednesday, or Thursday, whenever I release the video, I'll be releasing a video where I actually take apart one of these old power supplies, actually for use in these Back to Basics videos. But anyway, you'll notice that this is going to look somewhat familiar. It looks like we've got a half-wave rectifier up there. But here's where things get interesting. We're going to center tap this transformer. And we're just going to jump that over there. And then we're going to come out here, and that's going to be our load. So, what have we done here? Well, we've taken the waveform that's coming out of this transformer, cut it in half, and run it through two different half-wave rectifiers. So if we would have 12 volts typically coming out of that transformer, or whatever the transformer's output voltage is, our load is actually going to be 6 volts. Now how does this work? Well, if you measure from this point to this point on this transformer, you're going to get a 6 volt peak-to-peak signal. And if you measure from this point to this point on the transformer, you're also going to get a 6 volt peak-to-peak signal. Now, if I had a sophisticated enough oscilloscope to show you that, I would take two different channels on the oscilloscope and make this the ground, measure here and measure here with the probes. And what we would see is two 6 volt signals that are 180 degrees out of phase. So our signal on the oscilloscope would look like that. And in fact, let me redraw that real quick. So let's redo our graph, only I'm going to make use of multiple colors. I didn't quite draw my graph evenly there, but you'll get the idea. And then the other channel would look like this, because we are referencing this side to ground, or the center of it to ground. So when this signal is going positive, this signal is going negative, and vice versa. So what happens when we run that through the diodes? Well, as we saw last week, when we run an AC signal through just one diode, we're going to have a graph that looks like this, right? Oh, I should still be doing different colors, because that would be smart. So anyway, we'll say that this side is the green side. So when this side is going positive, the diode conducts current, and we get a bump. And then when the signal goes negative, current can no longer flow through that diode, so nothing happens down here. But then when the signal goes positive again, we get another hump on our sinusoidal. Now, what's going on the other side? Well, like we already said, when this side is going positive, this side is going negative. So nothing happens here because the diode won't conduct. But when this side is going negative, this side is now going positive, and we'll get a bump, like so. And then we're going to have a 6 volt rectified signal. which is just these bumps. Then we can throw a capacitor in there, and then we'll get ripple. But we're going to talk about ripple and diode drop and all of that stuff next week. Right now, we're just looking at what the ideal circuits do. Now, the other version of a full wave rectifier is also known as a bridge rectifier. Now, you've probably heard that term before. I've talked about them. And that is a much more... Hang on a second, I've got a gnat attacking me. Anyway, it's a much more efficient way of rectifying AC signals, because as you can see from our previous drawing, we were generating 12 volts using the transformer, but we only getting 6 volts out, so we were losing 50% of our current. So anyway, let's have a look at a full wave rectifier. So we're going to have an AC signal here, and that gnat is still attacking me. And then the thing that I hate to draw, which is a bridge rectifier. So let's see. I have a drawing off camera to help me remember how to do this. Okay, and then this will come over here. We'll go over to that. And then we'll go like this. And that needs to be pointed in this direction. Like so. Right? Right, okay. And then this comes over like this. And like this. And then we'll have our load here. Now this one is a lot more efficient because it doesn't waste half of your signal. So when we have our incoming signal that looks like this, during the positive half cycle, current is going to come over in this direction. It's going to flow through this LED and then out. And then current is also coming through here, over to here, through here, and then out. So that's positive half cycle. So that's when we get on our output signal, we're going to see a bump on our sinusoidal waveform. And then during the negative half cycle, the negative side becomes what would be considered the live. So we've got a positive half cycle coming through here, and then through this diode. And why is this being so juicy? Good grief. Okay. There we go. That's more like it. And then, of course, during the negative cycle, so current is flowing through here. Wow, that is really weird. I've never seen a dry erase do that. I've completely lost my train of thought. Anyway, so then we've got a positive wave coming through there, because we've basically used these diodes to trick our reference to ground to switch polarity. And then current is going to come back through here, and then up through here, and then over through here, and then out through there. And that way, we don't actually waste any of our signal. If we've got 12 volts AC coming in on this side, we've got 12 volts rectified signal coming in through this side. And it's much more efficient because we're not wasting half of our waveforms. All right, so the only thing that's really left to do is a practical demonstration. And I don't know why I'm erasing this, because I'm actually going to be putting it away. But I may as well erase it just to keep it clean. So, I'm going to do a quick jump cut while I set up for the practical demonstration. Alright, so this is the part that the disclaimer worked about. We're now playing around with an exposed mains voltage transformer. Don't try this at home, I know what I'm doing. Anyway, so right now we've got the power off. I have the oscilloscope tapped off. I tapped off a couple of leads here to the outputs of the transformer. Now, let's go ahead and have a look at the signal. Now, what we've got here is a basically 12 volt AC signal. And that's good. That's where we're supposed to be here. Now, if I take this and I look at the center tap, we're going to see that we now have a voltage max of about 6 volts. Now, you're probably thinking, but if it's a 3 volt transformer, why do we have 6 volts after cutting it in half? Well, we have to cut it in half again, remember, because we need to remove this bottom peak. So, if I go over, and I believe this should work, if I go to here, yes, we're going to see a 3 volt peak. Well, 3 volt average after we've removed the bottom peaks. And if we go over to this side, we're going to see again a 3 volt average because we've cut off the bottom peaks in the other direction. Now, just for fun, I'll go over here to the leads of the post-rectified signal. We'll go ahead, clip the leads on, and we're going to see here a 3 volt average full wave rectified signal. I just realized I don't think we actually saw the half wave rectified signal here, did we? No, we didn't. I can make it so that we can see that, but I already demonstrated that with a different transformer. So, now, just for fun, I'm going to show you a bridge rectifier in action. Let's go ahead and turn that off while I clip these leads on. So, I'll clip one lead to that side of the transformer, and I'll clip one lead to the other side of the transformer. And then I'll bring in this little bridge rectifier that I found. Now, this bridge rectifier has the AC signal coming in on the two center pins, then the positive and the negative on the outer pins. So we'll do that, and we'll do this, and then we'll do this, and then I'll turn it back on. And let me get rid of the signal here. Now you can see what we've got coming out now is a 6 volt signal, which is what we would expect from rectifying the 12 volt AC. Let's make that go away real quick, and we can see the nice full wave rectified signal there with a little bump there. I'm not too sure what's going on there. There's some parasitic capacitance going on that's smoothing down one peak of the rectification there. But yeah, you can also see the frequency goes up to 120 hertz because we're basically doubling the number of cycles by doing the full wave rectification. I forgot to mention that earlier. Anyway, so that's just your basic introduction to full wave rectifiers there. If I left anything out or made anything unclear, please start a discussion in the comments below. If you haven't already, consider clicking here to subscribe. Right over here will be a video that YouTube thinks you'll find interesting. Over here will be the Back to Basics playlist, and right here will be the Patreon link, which you can use to support further videos like this one. Thanks so much for watching, and we'll see you next week. Bye-bye.